This video is part of a series on the xv6 operating system kernel. There are a number of functions that implement the file-related system calls, and these are coming out of the file sysfile.c. There are quite a few functions, and in the previous video, that is part 1, I covered some of them, and in this video I will continue. And in particular, I will be covering the following system calls: open, make node, make directory, and pipe. The exact system call is a bit complicated, and I will handle that in a subsequent video. Okay, let's continue with these functions. Now let's look at the create function. This function is used to create a file and add it to some directory in the file system. It's passed a type code that indicates what kind of file we want to create, either a directory file, a regular file, or a device file. If we're creating a device file, we need the major and the minor numbers, so these will be something. For other kinds of files, for directory files and regular files, these will be passed in as 0 and not used. We're given the path name here as an argument, and that tells not only what directory we're adding it to, but the name as well. So for example, with this file name, we can see that we're adding a file called xv6 to some directory, in this example, user bin. On success, we will return a pointer to the newly created file, or more precisely to an inode for the newly created file, and that inode will be locked as well. If there's a problem, we'll return null. Create is called from exactly 3 places. It's called from the open system call, it's called from the make node system call, and it's called from make directory. And for the make node system call, it's for adding a device file, and so type will be device. For make directory, we're creating a directory, so type will be directory. And finally, the open system call has the option to open a file and create it if it doesn't exist. So when called from open, the type will be file. So we're passed in this path, and the first thing we do is call name iParent to parse this path name. So it will identify the final thing in the path name and store it in this variable name. So this local variable name will contain xxx. And then the prefix of the path name will be a directory, and that directory will be opened, and the reference count for that inode will be incremented, and dp will be set to a pointer to the inode. If everything's okay, then we'll keep going, but if we had a problem, then this will return null and will immediately return null. So we're going to be modifying this directory. We begin by locking it. The next thing we do is we look up xxx in this directory to see if it's already there. Okay, if it's already there, this will return a pointer to the inode for that file, and we'll set IP, and it will be something that's non-zero. So we do this code if the file already exists. And if this thing returns null, then we don't have the file, so we'll go on here to create the file. But it might be okay for us to have the file. In particular, if we are called from open, then it would be the case that we've had the flag to create the file if it doesn't exist. And if that's the case, we might have an existing regular file. Okay, so we check the type field of the file that does exist. And if it's a regular file, well, that's okay. It already exists. We'll go with that. Or if it's a device file, that too is okay. So we'll go with that. And in that case, we'll return IP. But if we were called to make a device file or make a directory, then this is going to be false and we'll return null. But if we find that it's okay, we will return IP. First, we have to lock it before we check the type field, and then we will return with it locked. And before we return, we will unlock the directory, okay? And we'll return either way here. And so if it's not okay, that is if we're called from the make node system call or the make directory system call, and we've already got something, then we need to return null. So we're going to both unlock the directory and unlock the file that already exists and just return null. Okay, so we've got the directory file locked at this point, and we've determined that the file doesn't exist. So at this point, we call ialloc. Ialloc will allocate an inode and will increment the reference count and will set its type to whatever we're passed in here. And so now we've got the inode in existence, and assuming that that works successfully and doesn't return null, we keep on going. Now we lock the file that we've just created because we're going to access some fields. First of all, we're going to set its hard link count to 1, and we're going to fill in the major and minor numbers, which will be important if it happens to be a device file that we just created. Then we're going to see whether the thing that we're creating is a directory file. If we have just created a directory file, we need to add entries into the directory for the dot and dot dot files. So that's what we're going to do down here. But remember that the hard link count in a directory situation will include the hard link from a child to its parent. So here we are increasing the count of hard links to the directory that contains xxx. And that's what happens here, and that's why we do that. And then since we've modified the directory that we're adding to, we update that. And then we are going to add entries for dot and dot dot. So we call directory link first for dot, providing the I-number of the file that we've just created, and then for dot dot, providing the I-number for the directory itself. And if something goes wrong there, then we panic, but otherwise we keep going. Now at this point, we need to add xxx to the directory itself. So here we're calling directory link yet again, passing it a pointer or to the inode for the directory that we're adding xxx to, as well as the name xxx and the I-number of the file that we just created. So presumably that will return something, and if there is a problem, then it will return -1, and we can panic. But otherwise, we're pretty much done. We still got the directory itself locked, so we need to unlock it, and we also incremented the reference count when we called name iParent, so we need to undo that as well with a put. So we do that here, and then we return a pointer to the newly created file, and it will be locked at this point. Now let's look at the make directory system call. It's passed a path name, and it's just going to create a directory file. So here's the code for sys make directory, and basically it's just going to call create, which we looked at. So it's pretty straightforward. We begin by putting everything in a transaction. So we have a begin op and an end op. And if there's a problem, we'll return -1, otherwise we'll return 0 to indicate that everything's okay. We begin by looking at the first argument, and it is the path name. So we're going to call argument string to copy from the user's virtual address space into this local variable path, the path name. And then we're going to call create, providing it that path name. And the type code will indicate that we want to create a directory file, and we pass in the major and minor numbers as 0. And if that works, it will set IP to be a pointer to the inode for the newly created directory file. If there's a problem, it will return null, and we immediately end the transaction and return -1. But if it's succeeded, well, we don't really need to do anything more. So we have locked this inode, so we need to unlock it and then decrement the reference count for the inode. And so we do that here, end our transaction, and then return 0. Now let's take a look at the make node system call. It's very similar. It's passed a path name and will create a file, but it will create a device file with the given major and minor numbers, returning 0 if everything's okay and -1 otherwise. So here is the code for make node. And it's really quite similar. We have a transaction, and if everything's okay, we return 0. Otherwise, we return -1. We have 3 arguments. The first one is the path name, so we call argument string to grab that and put that string, move it from the user's virtual address space into this local variable path. And then we get the next argument and move that into the local variable major. And then we call argument argint to get the last argument as a number, an integer, and move it into the minor variable. Now that we've got those, we can just call create and provide it the path. And this time the type is device, and we provide it the given major and minor numbers. And again, if there's a problem, it will return null, in which case we terminate our transaction and return -1. But if everything's okay, it will return a pointer to the inode for the newly created file. And that file is locked, so we need to unlock it and decrease the reference count and in the transaction and return 0 for success. We are now in a position to look at the code for the open system call. Remember that in Unix, open is passed a path name, that's the name of the file to be opened, as well as an integer that's called the flags value. And that value has some bits defined in it that tell what to do in certain situations. And the system call returns the file descriptor. That's the small integer that we'll be using in system calls like read, write, close, and so on. Now, this flags value has this definition here for xv6. In real Unix, this is a little bit more complicated, so you can look at the documentation for that if you're concerned about what's going on in production operating systems. But here's what xv6 does. It has the flag word defined with several bits. If this bit is 1, then the file should be opened write only. So write only is that bit. If this bit is 1, then the file should be open for reading and writing, and that's this bit. And if this bit is set, we should create the file if it doesn't exist. And if this bit is set, we should truncate the file to size 0 if it exists. And finally, we have this read only, which is no bits set at all. Okay, now let's try to walk through the code for the sysopen function, which implements the open system call. It will be returning the file descriptor integer. It begins by looking at its arguments. The function calls argstring to move the path name, which is the first argument, to the variable path here, which is a local variable from the user's virtual address space. And then it calls argint for the second argument, and it stores the flag integer in this local variable called O mode or open mode. If there's anything wrong, we immediately return -1. Otherwise, we start a transaction. We're going to possibly be creating a file, so we will be modifying the disk. So we need to have a transaction going. Now, the next thing we have is an if statement. We look at the create bit in the flags value, and if that is set, we do this, we call create. And if it's not set, then we call name I. Create will be passed a path name, and it will try to open the file if it already exists. And if it doesn't exist, it will create it, and it will create it as a regular file. If it creates it or opens it successfully, then it will set IP to point to an inode representing that file, and it will not only increment the reference count for that inode, but it will also lock that inode. So I'm drawing 2 lines here. If there's a problem, though, it will return null, and we immediately end the transaction and return -1. Otherwise, if the create bit is not set, then the file had better exist. So we call name I and provide it the path name, and it will find that file and allocate an inode in memory and return a pointer to that inode with the reference count incremented. So that's why I draw 1 line here. If there's any problem, that like the file doesn't exist, then it will return null, and we in the transaction return -1. Next, we lock that inode. So in either case, we've got the file locked. If the file already existed, then we check to see if it's a directory file. We're allowed to open directory files, but only in read-only mode. So here we're checking to make sure that the flags word is all zeros. That is, the write-only or the read-write flags are not set. We're not trying to create it, and we're not truncating it. So we're only allowed to open it in read-only mode. And if anything's wrong there, we immediately unlock it, and we decrement the reference count in the transaction and return -1. If the file was opened and it was a device type, oh, well, that's okay. We do a quick check to make sure that the major number is in the legal range here. And if there's a problem there, we would unlock it, decrease the reference count in the transaction, and return -1. Now we're going to, we've got an inode, either for a directory or regular file or a device file. And what we need to do is find a slot in the open file array for the proc structure for this process. And we need to fill in that value with a pointer to a file structure. So we need to allocate a file structure as well and set its IP pointer to point to this inode, whether it's a directory file, a regular file, or in this case, a device file. So that's what we're doing here. We call file alloc to create the file structure, and we set f to point to that file structure. And then we call fdalloc, and fdalloc will look through the array and find an empty slot and set that to point to the file structure and increase the reference count for the file structure. So if there is any problem with either of these, that is, we can't allocate the file structure and it returns null, or there were no available slots in the open file array, then we will get rid of the file structure if we allocated it by calling file close. And in either case, we unlock the inode and decrement the reference count in the transaction and return -1. Okay, but assuming everything's okay, we continue. If the type of the inode that we've just opened is device, then we've got sort of this situation down here where the inode points to a device. What we need to do is set the type of the file structure that we've allocated to device and copy the major number to the file structure. So that's what we're doing here. We are setting the type to device and copying the major number from the inode to the file structure. Otherwise, we've got a directory file or a regular file. And so in that case, we need to set the type of the file structure to inode, and we need to initialize the offset to 0. And that's what we do right here. We set the type to inode, and we initialize the offset to 0. Finally, we need to fill in the IP pointer in the file structure to point to the inode, whether it's a directory or a regular file, or whether it's a device file. We need to set the IP field to point to the inode structure, and we do that here. Then we need to set the readable and writable flags in the file structure. So here we are looking to see whether we have write-only. We make sure that that bit is 0. If it's 0, then either we have a read-only file or a read-write file. And in that case, in either of those cases, the readable flag should be set to true. So that's what we're doing here. And then we look at the write-only bit. If it's set, or if the read-write bit is set, then we are allowed to write to this file. So we can set the writable flag to true. And finally, we look at the truncate bit. If the truncate bit is set in the flags value, and we're looking at a regular file, then we can call itruncate, and that will truncate the size of the file to 0 and release any space it's occupying. Now at this point, we've got the file, the IP, the inode locked, and we've got the reference count incremented. So we need to unlock the inode, but we will keep the reference count incremented, okay, and return the file descriptor. We keep the reference count incremented because we now have a pointer. We stored a pointer to the file structure in the inode, and we stored a pointer to the we stored a pointer to the file structure in this open file array, and we stored a pointer to the inode in the IP field. So we do have a pointer to the inode, so we need to keep the inode's reference count incremented to indicate this pointer has been added to the inode. And so I believe that ends the code for the open system file, So I believe that ends the code for the open system call. Next, let's take a look at the pipe system call. In Unix systems, including xv6, the pipe system call is passed a pointer to an array, and that array has two elements. It will create the pipe, and it will return the file descriptors for the read and the write end in this array. It will return 0 if everything's okay and -1 if there's a problem. So let's look at what's going on here. Here I'm showing a proc structure for some process, and it's got an open file array that has some elements already filled in. And this system call will allocate a pipe structure as well as two file structures shown here and here. And then it will fill in pointers from the open file array to these file structures. So here we've created a pipe structure, and this is the read end. This file structure represents the read end, and the readable flag is set to true, and the writable flag is set to false. And you can tell that this is the write end because the writable flag is true, and the readable flag is set to false. But both contain pointers to the pipe structure, and the reference count for both is 1. And then what this system call will do is it will search the open file array and find the first unused slot and make that point to the read end, and it will find the next unused slot and make that point to the write end. And then it will save in this array the file descriptor for the read end. Well, that was 2, so we'll save 2 here. And then it will save in the second slot of this array the file descriptor it used for the write end, which was 5. This array is a fixed size array of 2 elements. Each one is big enough to hold an integer, so the total size of this array is 8 bytes, at least in xv6. Next, let's look at the code for syspipe, which implements the pipe system call. There's no activity on the disk, so we don't see any transactions in this particular function. We're going to begin by calling arg-adder to get our first argument. That's the virtual address of this FD array. So we are going to store that virtual address into this local variable FD array. And if there's any problem, we return immediately. Next, we call pipe alloc. And what pipe alloc is going to do is allocate this pipe structure as well as these two file structures and set this thing up here. And it will return pointers to the read end and the write end, that is the pointers to the file structures for the read end and the write end, by setting these variables here. If there's any problem, it returns -1 and we return immediately. Now we have got these three structures allocated, and we're ready to fill in these pointers here. So we're going to call fd-alloc to find a slot in the open file array and set it to point to the read file structure. And then we're going to call fd-alloc again to find another slot in the open file array and fill it in to point to the file structure that represents the write end. And then we're going to save these two file descriptors in fd0 and fd1. Now, I have no idea why we're setting fd0 to -1 here, because whatever happens, the first thing we do is call fd-alloc, and it's going to return something and modify fd0. But in any case, here if anything goes wrong, that is either of these returns a -1, then we've got a problem and we need to deal with it. So if we've got a slot for the read end, but failed on the write end, then FD0 will be something greater than or equal to 0. And so we need to eliminate that. We need to restore it to be null. So that's what we do here. But in either case, we close both file structures. And remember that with the pipes, when we close an end of the pipe, it will eliminate that file structure. And if it's the last pointer to that pipe structure, it will free up the pipe structure itself. So on the second call to file close, we close the last end of the pipe, and that will free the pipe structure as well. Then we return -1. But assuming that we were able to store these pointers into the open file array, we now have FD0 being 2 and FD1 being 5. So we need to store those into the FD array in the user space. So this value right here is the virtual address of this FD array, and page table indicates the virtual address space. So we're using copy out to copy from the kernel space, namely the value that's stored at FD0. And the size of FD0, well, that's an integer, so that would be 4 bytes. And so we're going to copy 4 bytes into the FD array at offset 0. Okay, and then we're going to copy the value of FD1. Okay, and we're going to copy, again, 4 bytes, and we're going to copy it to the virtual address space. And this time we're going to copy it into offset 4, that is the beginning of FD array, plus the size of the first element. So the beginning of FD array plus the size of the first element will be the address of the second element in the array. So here we're storing the 2 and the 5, the 2 file descriptors, that is, into this FD array in user space. And if there's anything wrong here, well, we need to return those file descriptors to null. So we store a 0 in this element here and a 0 in this element there. And then we close the read file descriptor and the write file descriptor as before and return -1. But if these two copy outs worked fine, then we skip that and return 0 to indicate success. Okay, the final system call that we haven't talked about is the exec, and that's pretty involved. So I'm going to do that in the next video. That's all for this video. I'll see you in the next video.